Hello and welcome to IB and A-Level Learning Center with Mr. Tai. In this video, we'd like to help you and explain in detail how to solve the problems related to the topic about waves and wave phenomena such as diffraction, interference, and stationary wave. The first question here that we'd like to explain to do is the question number 6 in the paper this summer a few months ago in May 2024, and the paper 2.2, the second version. Question 6, light on a single frequency is incident normally on the diffraction grating. An interference pattern of bright and dark fringes forms on the semicircular screen shown in the figure 6.1. Người ta dùng laser để mà chiếu vào một cái diffraction grating và nó sẽ tạo thành một cái pattern ở trên một cái tấm màn có dạng nửa vòng tròn như thế này. The light has a wavelength 520 nanometer. The separation of the lines in the grating is 3.8 times 10 to the power negative 6 meters. Determine the total number of bright fringes formed on the screen. To answer this question, the total number of bright fringes formed on the screen, we need to use this formula. This is an illustration of the pattern formed by the grating, and each position here associated with n equal 1 and 2 are the maximum fringes. The angle we are talking about is this angle, theta 1 or theta 2. Theta 1 is the angle made by the line from the laser to the the center of the spectrum, which is the central maxima, and to the first maximum below the central maxima here. The formula is tan of this angle theta, which is determined by the distance between the central fringe and the first maximum, which is h, divided by d. D is the distance between the grating and the screen. And because the angle, when the angle is small, we can take an approximate, which is the tan of this angle theta is approximately equal to the sine of the angle. The formula, the wavelength, is determined by d multiplied with sine theta and over n, where d is the distance between two successive slits on the grating. If the grating has like 1000 slits on 1 millimeter per millimeter, then this d in this formula is 1 millimeter divided by that 1000. Of course, the unit here is millimeter, and therefore we need to multiply with 10 to the power negative 3 to convert it into meter. So that on both sides of the equation, the left side, the wavelength, can be calculated in meter. The right side, the d, calculated in meter. Sine theta, of course, it has no unit, and n has no unit there. So if we calculate the distance d here in meter, then the length is determined in meter. And when d is calculated in millimeter, then of course the wavelength lambda is also calculated in millimeter. So we will do this question as follows. The formula is lambda equal that d distance, which is 1 millimeter, divided by the number of slits per millimeter, multiplied with sine of the angle divided by the number n. To find the total of the bright fringes formed on the screen, we will calculate the maximum order of the most outer, meaning that the bright fringe, which is closer to the outer here. Okay, this is the maximum n, and we have other maxima such as here n equal 1, here n equal 2, for example, and so on. So the point is to calculate the value of the maximum n here, and it is determined by that d multiplied with sine of the maximum angle. We assume the maximum angle is 90 degrees, which means we assume that the maximum is like here at this point, and this angle is 90 degrees. Okay, divided by the wavelength lambda. Okay, now substituting the value into this formula, the grating separation, this thing is d. 3.8 times 10 to negative 6. Sine of 90 is 1, and the wavelength lambda is 520 nanometer converted into meter so that it has the same unit with the d here in meter. So multiply this wavelength with 10 to the power 9 minus 9 and then use a calculator to find the value of maximum n. Okay, the top d is 3.8 times 10 to the power negative 6. Sine of 90 degrees is 1, and then we divide the whole thing here by the wavelength lambda, which is 520 multiplied with 10 to the power of minus 9, and the result is 7.3. 7.3, and therefore we need to round that number 7.3 down to 7, which is the maximum. The result is 7.3. So the maximum number is 7 here. I should have drawn many other fringes in between, 1, 2, 3, 4, 5, 6, 7, etc. like that. Okay, so there are 7 maxima on the top part of the string, and similarly there will be 7 maxima on the lower part, and therefore the total number of the right fringes is 7 times 2, the top and the bottom added together, 7 plus 7, and then you need to add with 1, which is the middle, the central fringe, and therefore the total number is 15. Okay. Moving on, question 2. The light is replaced with the red light of single frequency. State whether the frequency of the red light is greater than, less than, or the same as the frequency of the original light. Replace the red light, replace with the red light. So what was the initial color or the wavelength that we used? 520. The 520 is like the yellow color. We didn't know, it is not stated in the problem here, but I think this number 520 is the yellow color, which is shorter than the red line. The red line wavelength is about 700 nanometer or 650, like something like that. So which means that the red line here has a lower frequency. The red line has lower frequency compared to the yellow line. Say with the frequency red line is less than the same as the original line, the yellow. So we just need to write one word, which is lower frequency. One word only is enough. Okay, check the answer. A number of fringes formed 15, correct. Less, just like that. The frequency of the red line is less than the frequency of the original light. You can write a whole sentence like this, or just one word, noting carefully the statement, the question, comparing the red line with the original light. Question 2. State and explain the effect of this change of the number of bright fringes formed on the screen. Calculation is not required. 2 marks, 2 marks meaning that you have need to answer 2 ideas. 2 ideas. Okay, and those 2 ideas are the central maximum is the same, meaning the position the same. The intensity might be the same. Assuming that the intensity of the red light is still the same with the original light, the position, of course, of the central fringe is the same. And the second idea is that the fringes get closer to each other not closer. Okay, the formula for the separation, the distance between 2 successive fringes is the wavelength multiplied with the distance between the grating and the string divided by the small. This is a formula for the double slit, not the grating. For the grating, you have the angle theta determined by sine theta equal to n lambda over d. Okay. So because psi of a function is an increasing function, hàm số đồng biến, which means the psi increases when the angle increases, which is the unit circle. So as the angle increases, the psi of that angle also increases. And therefore, when we replace the wavelength of the yellow color by the red color, the wavelength lambda here get greater, and therefore for the same order, the same number of n, for example, n is 1 or n is 2, the wavelength increases, the sine of this angle also increases, meaning that on the new pattern now with the center n equals 0, we see the yellow color, the first position, the position of first maximum, we see the position of the red, meaning the angle is greater. The red color will have a greater, angle, and we can conclude that the distance between these fringes increases. Fringe separation, we can say that fringe separation increases. In other words, they get further away from each other. Okay, and the second idea is the position of the center fringe remain the same. I mean the same position, but the thickness, the width of the fringe can change. I'm not so sure how it changes. Possibly wider, but it's not necessary to be mentioned in the answer. Center fringe remain at the same position. And get wider, I believe. Wider, okay? We can check answer. Longer wavelength, so number of fringes formed is less number of fringes, fewer fringes. Okay, has longer wavelength. That is the explanation. The separation increases, therefore fewer number of fringes. And the explanation is one other marker, because the sine of the angle is proportional to the wavelength. And the red wavelength has the longer wavelength compared to, which is okay. We have to mention that this wavelength is lower to get the full marker to the wavelength, which is now shorter. Sorry, longer wavelength, which is longer there. Okay, the next question 7 is not about wave. Let's move on to another paper also about wave. Let's move on to another problem about wave, which is also in this summer 2024, question paper 2-3. Okay, question number 4. A progressive transverse wave traveling from left to right is shown at an instant of time on the figure. The direction is from the left to the right. R and T are points on the wave. R here is a crest, and T is a equilibrium. T here is equilibrium position. State the phase difference between the points R and T. Okay, the answer is simply 1/4 of a period. Wait, from this point R to this Q is 1/4 period, which is pi over 4. From this R here to the bottom, the top here, let's call R dash, the phase difference is pi. This is not pi over 4, pi over 2. Yeah, and here the phase difference will be 3 pi over 2. So that when you go to this point, let's call it Q, the R and Q have the same phase, meaning the phase difference between them is 2 pi, 360 degrees. So the answer, you can answer two ways, 3 pi over 2 or pi over 2. 3 pi over 2 or pi over 2 is the answer. Oh, given here the unit in degree. So yeah, we need to answer that in degree. 3 pi over 2 is 270 degrees. Now let me remind you about a formula to calculate the phase difference between the 2 points. You need to determine the distance that the wave travel between those 2 points, such as from R to T. Calculate that distance, and then divide the wavelength lambda, and then multiply with 2 pi, or if you answer the question in degree, then replace with 2 pi by 360 degrees. In this case, the distance between the 2 points R and T is from R here to R dash here is half wavelength. So that is half and 1/4 wavelength. 1/2 wavelength here, and then add 1/4 wavelength, and then divide the wavelength times 360 degree. Anyway, the point is to understand it that way, between R and R dash here, they are out of phase by 180 degree, and between this R dash and the T is 90 degree more, and therefore 180 degree. You add it with 90 degree, with 90 degree, and you get 270 degree. Question B. On the figure, draw an arrow at the point T to show the direction of movement of the point T at the instant shown. The direction of movement. Okay. To answer this question, again, this kind of question, okay, you just need to draw a new wave. The point Q here is moving to the right in the direction that the wave travel. So you draw another wave like this right below, like at a very small time interval later, like 0.1 second or something, which is very short time interval, The position of the new wave is like this. Okay. There. This is the new wave, which means the point Q is moving from this peak to the next position here, and therefore this point T must move downward to the new position here. This is the new position of T, and therefore the answer, you just need to draw this single with only one vector. Do not draw anything else, just one vector like this. Okay, that's the answer, which is vertically and downward. There, downward. Calculate the frequency given the speed 0.27 meter per second and this distance. This distance is 3/2 of a wavelength, right? Because from R here to next point here, let's call Q, is one wavelength. So this is half wavelength, half wavelength, and 1/4 wavelength. 3/4 wavelength. Okay, so that 3/4 wavelength, 3/4 lambda, is equal to 0.62, and therefore the wavelength lambda is 0.62. 62. Multiply with 4 and divided by 3. 0.83 centimeter. Multiply 10 to negative 2 meter, meaning that 0.83 centimeter. The frequency is calculated by lambda equal the speed over the frequency, and therefore the frequency is the speed over the wavelength. The speed is 0.27, and the wavelength is 0.83 here, 33 there. Question D. The wave in a water wave produced by a dipper S1 attached to the vibrator in the ripple tank. An identical dipper S2 is attached to the same vibrator. The two dippers produce an interference pattern on the water in the tank, shown in the figure. The wave crests from each source are represented by the solid lines on the figure, and the wave troughs are represented by the dashed lines. Những cái đỉnh sóng nhô lên thì vẽ là cái đường liền nét, còn những cái chỗ mà sóng nó lõm xuống gọi là trough thì nó vẽ bằng những cái đường đứt nét. Có nghĩa là nếu như hai cái đỉnh sóng, hai cái đường liền nét gặp nhau thì nó sẽ tạo ra một cái đỉnh sóng cao hơn. Và nếu hai cái đường đứt nét gặp nhau thì nó sẽ tạo ra một cái hõm sóng sâu hơn. Còn nếu mà một cái đường liền nét, một cái crest gặp một đường đứt nét là trough thì nó cancel nhau ha. Okay, in this problem, when the two solid lines meet each other, for example, this point, one solid line, meaning one crest, meet another crest, the two crests combine and result in a higher crest, a greater amplitude upward, in the upward direction, greater crest, okay? And when the two troughs, which are the two dashed curve like this one dash curve and another dash curve here, the two troughs meet each other, it will form a even deeper and greater trough. Those 2 points, for example, this point is one maximum, this is also a maximum, but in the opposite direction, okay? And at one point, when a crest like this meet a trough, which is a dashed line, dash curve, then we see a stationary point, which is the minimum of the interference pattern of the two waves. These are the two coherent waves on the surface of a still water surface. They have the same frequency, of course, the same amplitude. The question at the point P here, which is the intersection point of one crest and one trough, it is a minimum. One crest and one trough is a minimum destructive interference. Describe and explain the amplitude of the resultant wave at a point P. Okay, three main idea, The amplitude described the resultant wave at P has zero amplitude. One idea, zero amplitude, because the two waves are out of phase. One crest and one trough. Two waves are out of phase. The phase difference is 180 degrees. They destructively cancel each other out, interfere with each other, destructively interfere and cancelling each other out. Of course, because they have the same amplitude, so the result is zero amplitude. Okay, let's see if this answer, including the three main areas, zero amplitude, out of phase, and cancelling, is enough to get the maximum mark, which is 3 marks. The structure interference, 1 mark. The phase difference, the path difference is half wavelength. The phase difference is 180 degree here. The same amplitude is can get you 1 more mark. Okay, so we can mention that. Cancel each other down. Out of phase and same amplitude. We need to add the word and same amplitude here, and same amplitude. So they interfere with each other destructively there to cancel each other out completely and result in zero amplitude. Okay, the next one is about electricity. I'll do that one later. Let's move on to another problem, which is in the winter last November and October and November last year, 2023, paper 2-3, question number 5. 2 point sources A and B produce coherent electromagnetic waves. The waves from A and B are emitted in phase, and have the wavelength lambda shown in figure 5.1. The lines on the figure represent wavefronts. All the points on wavefronts are in phase. On the figure, mark with a cross X the position of the interference maximum, label with cross Y, and the position of interference minimum. Okay, the wavefront, when they intercept with each other constructively, you can choose any of the intersection between these wavefronts. For example, this point, or this point, or this point, any of those points are the Y, meaning the maxima, when the two wavefront, the two crests meet each other. And so you can choose like this point, or this point, or any other intersection point. Okay, and the point which is the minimum, labeled by the Z. Okay, we need to label with the X letter, not a dot like this, an X letter, and this is the maximum. The minimum will be in between with the intersection of one wavefront, the crest, and the trough, which is the middle like this, a crop. So you can label this point Z right next to it, or can be like here, Z. Okay, yeah, just like that. Let's check the answer. Question number 5. Cross label Y drawn of any position where the wavefronts cross the intersection between the any two wavefronts. Okay, or centrally in a diamond shape form between any adjacent wavefront from A and B. Okay, and the Z drawn on a wavefront from one source at any point midway, the point here, midway between adjacent wavefronts. Okay, the answer is like that, which is definitely correct here. Question B. The waves in the air have the wavelength of 2.9 times 10 to the power negative 5 meters. An interference pattern is detected along the line parallel to AB and at a perpendicular distance of 140 meters from AB. Detected along the line parallel to AB. Parallel to AB somewhere. And the distance 140 meters from AB. Perpendicular to AB. Along a line parallel to AB. Perpendicular distance of... Okay. Horizontal line like this, parallel to AB. And the perpendicular distance between this line and AB is 140 meters. Along that line, calculate the separation A of the source AB. The spacing between adjacent interference maxima, adjacent meaning they are next to each other. Okay, so we can determine the two maxima on this line. One maximum is this point, and another one is this point, Okay, or it can intersect here. Continue drawing the curve like this, and another intersection point here, which means the distance between these points, or this point and this point, is 1.2 meter. Okay, that is the statement of this problem. 1.2, not meter, centimeter. 1.2 centimeter. That is the statement of this problem. Okay, what is the question? Calculate the separation A of the sources A and B. Okay, the distance between A and B. A is what they ask for, this distance. How do we determine that? Okay, the question asks to find the distance between A and B, and actually this kind of interference of the wave on the surface of the water is very, or we can say identical to the interference of the laser passing through the two slits in the Thomas Young double slit experiment. And for that double slit experiment, we have this following formula. The fringe separation, which is the distance between the two adjacent successive fringes, is the wavelength multiplied with the distance from the fringes to the string and divided by the separation between the two slits. And we will apply this same equation for this problem. We need to find A. Okay, so A is lambda d over s. Lambda, the wavelength. What's that value of the wavelength? Here, 2.9 times 10 to the power minus 5 meter. The waves in air have the wavelength. Oh, but that is in the air. How about the wavelength in water? We do not have any information about like the speed of the wave in the water or any other related, information to find the wavelength in the water with the wavelength in the air. And I think we can use this wavelength. That is the only information that we've got. Here, the formula. Taken that wavelength 2.9 times 10 to the power minus 5 multiplied with the distance between the slit, which is the sources of the wave, which is A and B, to the line. That distance is this thing, 140 meter. Okay, this thing of course is already in the meter unit, and the separation between the two adjacent maxima is 1.2 centimeter. We need to multiply 10 to the power negative 2 to convert it into meter, and therefore the distance A between A and B will be determined by this formula, this ratio calculation, and the value is 0.34 meter. 0.34 meter. Okay, this is the answer. 0.34 meter. State the principal region of the electromagnetic spectrum to which the waves belong. The region electromagnetic spectrum to which the waves belong. The wavelength here in the air, to the power minus 5 meter, it is longer, much more longer than the visible wave, such as the light that we see in the yellow color is like 500 nanometer, which is 5 times 10 to the power minus 7 meter for the yellow color, visible to the power 5, meaning the wavelength here is like 100 times longer than the visible light, and that thing longer can be infrared or radio. I don't know for sure it's radio or infrared, but I prefer the radio. I think 100 times longer. Okay, infrared. Infrared thì hẳn phải answer. Infrared hồng ngoại ha. Okay, one last question also about wave in the paper in 2019, question paper 2-3 in winter, November. Light waves emerging from the slits of a diffraction grating and coherent and produce a interference pattern. Explain what is meant by coherent. The meaning of coherent is that the wave has the same frequency, and even more important thing stated in the mark scheme is that the phase difference between the waves is constant. Phase difference is constant, or we can say constant phase difference. It is even more important than the same frequency. Interference. Okay, definition of interference is the combination, the superposition of the two waves, the two coherent waves. The superposition, or in other words, which is simpler, the combined combination of the two or more of coherent waves, in which the resultant waves has the displacement to be the sum, the total of individual displacements of individual waves. And the mark scheme say combination displacement overlapping meeting wave. Okay, of coherent waves in which the resultant wave, the displacement of the resultant wave is the sum of individual displacement. Question B. A narrow beam of light from a laser is incident normally on the diffraction grating as shown in the figure. Spot the lines of seen on the screen positioned parallel to the grating. The angle corresponding to each of the second order maxima is 51 degrees. The number of lines per unit length of the diffraction grating is this one. The number of lines per unit length. This is the wrong statement because the number of lines should be a number n such as 1000 or something. This is the grading separation, which is the small d, 1 meter divided by the number of slits on that 1 meter. Anyway, this is per meter. A lot of lines on 1 meter. On 1 millimeter, it is 670 lines per millimeter. So because 50 meter 1,000 times greater than millimeter, and therefore the number here is 10 to the power 5. Determine the wavelength of the light. Easy question. Just need to use the formula. The separation d of the slit multiplied with sine of the angle, which is 51 degrees, equal to n multiplied lambda. In this case, the number n here is the second order, which is n is 2. This n is 2. The lambda, the wavelength, is what we need to find. Okay, use a calculator. This d is 1 meter over that number, 6.7 times 10 to the power 5. And the angle is 51 degrees. So from this equation, you can determine the wavelength lambda pretty easily, which is 5.8 times 10 to the power negative 7. 5.8 times 10 to the power negative 7 meter. And do not forget to write the answer right here at the answering space. Minus 7 there. Okay. State and explain the change, if any, to the distance between the second order maximum spots on the screen when the light from the laser is replaced by the light of shorter wavelength. Change to the distance between the second order maximum spot on the screen. Okay, the formula that we use is d times sine theta equal to n, which is 2 in this case, multiplied with the wavelength. So when we use a shorter wavelength, this lambda decreases. Of course, d here is a constant. The sine of this theta angle is also decreases. The sine of this angle decreases, meaning that the angle will be less than 51 degree. Okay, stay and explain. The angle is smaller, the angle gets smaller, becomes smaller, or decreases. Because according to the formula of the diffraction grating interference, diffraction grating, what's it called? Diffraction, the name of the phenomena, because sine of the angle at which the second order maxima is determined. Maximum, meaning I'm talking about this angle, maximum spot is determined. This sine is proportional to the wavelength. We cannot say that the angle proportional to the wavelength, but the sine of that angle, okay, proportional to the wavelength, which is now reduced. The wavelength is shorter. Yeah, that's it. That's the answer. Distance, shorter distance, smaller angle between the second order maximum spot. Okay. So that's all. My explanation for the 4 problems in the recent paper relating to the topic waves, diffraction grating, and double slit interference. I hope that you find it useful. That can help you understand better this topic. And please leave a comment below if you have any question, or don't hesitate to contact me on the provided email. Thank you.